Have you ever seen the sun turn green? No, it's not an illusion. It's a rare, real, and stunning effect. And today I'll show you why the green flash happens, debunk some common myths, and teach you how to capture it yourself. The green flash is a fascinating confluence of astronomy, planetary physics, atmospheric optics, and even a little bit of global warming thrown in just for good measure. It's not a government conspiracy. It's a phenomenon of science that touches nearly every corner of physics, from the properties of black-body radiation to the properties of aerosols and even carbon dioxide. And no, it's not CGI or a camera trick. I've actually captured the green flash over 16 times using a method I'll share with you today. Over the next few minutes, you'll learn how to find the perfect conditions, use just 2 simple camera settings, and understand why this rare moment of emerald jeweled beauty occurs. Green flashes are real, and they're spectacular.
They're real and they're spectacular.
Recently, I had the honor of appearing on Andrew Huberman's Huberman Lab podcast, and we explored how the human eye perceives light. Now, Andrew's an expert in the human eye and neuro-optical systems, so it was a real treat to get to explore this phenomenon with one of the world's greatest experts. During our conversation, Andrew asked, could the green flash merely be a trick of human physiology or psychology? Today we'll explore why his hypothesis is not quite correct and explore the deeper science behind the phenomenon. Let's get started. The first time I saw the green flash, I was 18 years old, staring at the horizon during a picture-perfect sunset on the Pacific coast. That moment sparked my love for astronomy and made me want to capture these ephemeral emerald vistas for all my life. Now, sailors have been talking about these for generations. Jules Verne actually immortalized the green flash in a book called The Green Ray, calling it a signal of true love. But beyond the romance, or bromance, scientists have been fascinated by the green flash for centuries. It was dismissed as a sailor's myth until the 19th century, when atmospheric optics helped explain its origins. Yet even today, most people haven't seen it or even heard of it, and very, very few people can understand why it occurs. Now first, I want to take a quick detour. The sun's color. Why does it look yellowish white to our eyes, when in fact it's actually green? That's a hint as to the ultimate resolution of this atmospheric phenomenon. The green flash gives us an opportunity to explore a common misconception. What color is the sun really? Now, I actually did a poll on X, formerly known as Twitter, and I asked over 50,000 of my followers, what color is the sun? You'd think that would be a non-controversial question, but only 16% of people got it right. Well, the sun appears yellowish white to us. As I explained, its peak radiation output is actually in the green part of the spectrum. This is because the sun is a nearly perfect black-body radiator, an object that emits and absorbs at all wavelengths. The distribution of this radiation was first described in the early 1900s by Max Planck himself, and it's described now by what we call Planck's law, which has a peak wavelength that is inversely proportional to the object's temperature. The higher the temperature, the shorter the wavelength, or the higher the frequency. The sun's surface temperature is approximately 5,800 Kelvin, and according to Wien's displacement law, where the temperature T is in Kelvin, the peak wavelength for the sun is about 500 nanometers, or 5,000 angstroms. This puts it squarely in the green color of the electromagnetic spectrum. So why does the sun not look green? Is it because I'm smoking too much of that green leaf? No, it's because the sun emits light across the broad spectrum, and when this light combines from yellow to green to blue to indigo, violet, and even with red, it appears white, or slightly yellowish due to atmospheric scattering, which we'll explain shortly. Now, our sun is a star, and stars follow a very interesting color-temperature relationship called the Hertzsprung-Russell diagram, or HR diagram. Red stars like Betelgeuse are cooler, around 3,500 Kelvin. Now, blue stars in the same constellation of Orion, like Rigel, are much hotter, over 10,000 Kelvin. The HR diagram maps these relationships, revealing a star's life cycle and its energy output. The green flash is a complicated optical phenomenon resulting from refraction, dispersion, and scattering. Let's break it down step by step. First, refraction. When sunlight passes from the vacuum of space into the Earth's atmosphere, it bends due to changes in density. The Earth's atmosphere acts like a giant lens, and near the horizon, this bending is exaggerated because of the local appearance of the curved Earth appearing flat. Now, don't give any of you flurfers any ideas. The Earth is a curved surface, and that's actually also indicated by the fact that when you see the sun go below the horizon, as shown here, it's actually below the physical horizon, and that occurred at least 8 minutes ago, and actually more like 10 to 20 minutes ago due to the refractive properties of the Earth's atmosphere. Each layer of the Earth's atmosphere, shown here, has a slightly different refractive index. Objects with different refractive indices, whether it's glass or water or lead crystal, refracts light or bends light more strongly with higher and higher refractive index. The refractive index is related to what's called the dielectric constant of the material. So high dielectric constant materials like diamonds have very high refractive indices. They have very high dielectric constants. They're actually related by a square root function. Refraction at the horizon also depends on the optical path length, which increases dramatically as the sun approaches the horizon. This extended path causes the sun to appear slightly higher in the sky than it actually is, lengthening the time we see it and further enhancing refractive effects. Now we come to the second effect, dispersion. Dispersion is the separation of light into its constituent wavelengths. It's what you're familiar with a prism or a rainbow doing. Shorter wavelengths like green and blue bend more than longer wavelengths like red and orange. The refractive index for a wavelength lambda can be modeled using the so-called Cauchy equation. A, B, and C here are material-specific constants. As the sun nears the horizon, dispersion isolates green light for a brief moment. However, blue and violet light, which are refracted even more than green, are scattered out before they can reach their eyes due to scattering effects. The third major atmospheric optical effect is called scattering. In this case, it's called Rayleigh scattering. This explains why blue and violet rarely reach our eyes during the green flash. Rayleigh scattering is the effect of particles smaller than the wavelength of light causing scattering of the light, and it's very, very strongly wavelength dependent, except it depends as the inverse fourth power of the wavelength. So wavelengths that are roughly 2 times as long, like red compared to blue light, scatter 16 times more. This leaves a net deficit of blue and indigo light from the otherwise primary blackbody function, leaving green left behind as the shortest wavelength that's visible to the eye, and that ends up dominating what we see. There's another type of scattering called mi-scattering, or mi-scattering, M-I-E, caused by larger particles like dust and aerosols. This scatters all wavelengths equally because the particles are like giant chunks of light, so they scatter and block and obscure all light the same. This has the net effect of muting the green flash's intensity, particularly in polluted or humid conditions. There are many, many other effects, such as the famous mirage effects, where temperature gradients in the atmosphere bend light, creating mirages. You've seen that on hot desert roads, perhaps, or in wandering through the desert, searching for an oasis. The superior mirages, where cold air lies below warm air, can amplify the green flash by actually stretching it vertically or extending its duration. So-called inferior mirages can distort or even split the flash into multiple bands. You sometimes see that in layers where the sun will actually look like a pyramid or a ziggurat, a stack of horizontal slabs. Now the Earth's curvature plays a role as well. This is because the curvature is actually ensuring that the optical path length increases near the horizon, creating conditions for extreme refraction and dispersion. A flat Earth model would fail to produce these effects because the atmospheric thickness would remain constant across the horizon. There'd be no diminution or limb dimming as you get away from, say, the direct path between you and the sun. Now, in the beginning, I mentioned the effect of climate change. But what role does it play? The green flash is not necessarily associated with the green movement, don't worry. In fact, the green flash is a natural phenomenon, but human activity does shape it slightly in ways that make it more or less visible. First of all, when fossil fuels are burned, they release aerosols, tiny particles that contribute to mi-scattering, as I said before. This mutes all colors, including the green color, in highly polluted areas, like those neighbors to the north where Andrew lives, Los Angeles. But aerosols can also enhance sunsets, creating the deep reds that make the green flash even more prominent against the red or orangish hue on the horizon. Now, I'm not advocating for more carbon dioxide emissions, but as they continue, expect sunsets to get redder and the green flash to get slightly muter relative to what it would be in the absence of these aerosol particles. Now, there's a far more serious consequence that was discovered here at Scripps Institution of Oceanography by colleagues that work on atmospheric global climate change and the effects of cloud cover. You see, cloud cover is the bane of the green flash watcher's existence. The green flash cannot be seen when there are clouds anywhere near where the sun is setting on the horizon. And scientists here and elsewhere suspect that more climate change means more clouds, more moisture in the atmosphere, and perhaps a diminution or reduction altogether of the green flash phenomenon, depending on where you are. So this is also a reminder of how closely the Earth's climate and our atmosphere are connected through these moments of fleeting beauty like this atmospheric phenomenon. As I said in the beginning, during our 5-hour-plus conversation, Andrew Huberman hypothesized that maybe the green flash could be a physiological effect or psychological effect of the human's brain visual system. While our eyes are exceptional tools, the green flash isn't just visible to humans. It can be captured by digital cameras. This proves once and for all that it's a physical, optical phenomenon. Now I bring this to you as an example of what I call hammer theory. And that's the famous saying that when all you have is a hammer, everything starts to look like a nail. Now, Andrew has many tools in his toolkit. He has a deep understanding of human vision that has naturally shaped his worldview and his hypothesis of the origin of the green flash. But as scientists, he and I both know that our job is to test hypotheses with evidence. So that brings us to how you can capture the green flash yourself using a simple camera system. Now let's break down how to capture the green flash with both a smartphone and a DSLR. I'm going to give you just 2 critical settings for each. That's all you're going to need to focus on. Get it? First, let's start with your smartphone. Forget what you've heard about needing expensive gear. I've captured stunning green flashes with just my iPhone. And you could do it too, even if you're a heathen, with one of those Android devices. The first crucial setting is exposure lock. About 30 seconds before sunset, press and hold your finger on the brightest part of the sky near the sun. You'll see a lock indicator appear. This prevents your phone from constantly adjusting exposures, which would otherwise ruin the shot. The second key setting is RAW mode, not raw dogging. No, on an iPhone, enable Pro RAW in your camera settings. Android users, you can switch to Pro mode. This gives you much more detail to work with later. This is very significant when capturing something as ephemeral and subtle as the emerald-like green flash. Now, for DSLR or mirrorless camera users, we're keeping it just as simple. 2 settings, that's it. First, switch to aperture priority mode. That's usually indicated by A or A with a little V on your dial. Set it to about f8. I've tested most every aperture, and f8 gives you the perfect balance of sharpness and light gathering ability. Any wider and you risk overexposure. Any narrower and you lose critical light and it becomes too dim. Now the second setting for a DSLR camera is to lock your ISO or ISO at 100. Don't use auto ISO. It'll try to compensate for the dropping light and that will ruin your shot as well. At ISO 100, you'll capture the cleanest possible image with little to no digital noise to muddy the green flash. Now everything else can stay on default settings. White balance, leave it on daylight. Focus, set it once on the sun and leave it off. Image stabilization, turn it off if you're on a tripod. Now I only know these settings are successful because I failed thousands of times testing everything else. You don't have to learn it the hard way. These 4 settings total, 2 per camera type, are all you need to focus on. Just to recap, for smartphones, exposure lock and RAW mode, for DSLRs, f8 and ISO 100. That's it. Don't let anyone tell you it's more complicated than that. Next, what's the best place to view the green flash? Well, it's best viewed in locations with clear horizons and stable weather, like Hawaii or California's Pacific coast, because it's dry. Frequently there is also a desert. The green flash occurs at both sunset and sunrise, but it's much easier to see at sunset, as you're already tracking the sun's descent. It's very hard to know exactly where the sun is going to come above the horizon, and you need to catch that at sunrise and know exactly where it's coming up. It can be done, and some of you on the East Coast can catch this magnificent appearance. For my extremophiles out there, the South Pole offers perhaps the best place on Earth to witness the green flash. There, because the fact that the sun is slowly sinking towards the horizon, spiraling around, it actually takes hours to cross the horizon from the disk of the sun's bottom to the disk of the sun's top. That's only half a degree in angular diameter, but you can see that and lasting for several hours as it traverses the horizon, meaning you can watch the green flash for hours. But be careful, in order to be there, you have to be there at sunset, which occurs just once a year on March 21st. Now, if you miss the green flash or you catch it, I don't know which would be better or worse, you're going to have to stay there until November because planes can't get in or out of the South Pole between those 2 periods without their hydraulic fluids and their actual jet fuel solidifying and becoming an unworkable mess. So planes don't land or take off there in the winter, which is where you'd be there after you see the sun set. That's the beginning of fall, March 21st down there, and you won't see it again rise above until September 21st. I talk about that phenomenon in my first book, Losing the Nobel Prize. If you happen to catch the green flash yourself, you may make your friends green with envy. Now, I know if you've enjoyed this conversation, you're going to enjoy my conversation with Andrew Huberman on his podcast, but you're also going to enjoy these videos that I've made featuring the physics behind the eye, telescopes, and the secrets of stargazing. Click here, and I'll see you in our next adventure.